Good evening, everyone. A very warm welcome to everyone who have joined us today live for this session on NCERT Class 12 Exercises Discussion Series. Today we are gonna take up chapter number 8, which is electromagnetic waves. So, as you guys know, NCERT forms the basis for your Class 12th as well as NEET UG preparation. So we're gonna take up the exercise questions. There are total 10 questions for today, and we're gonna discuss the concept associated with each question and their solution in detail. So, a brief introduction about myself. I am Sashwat Mishra. I am a third year MBBS student at AIMS Raipur. Previous to this, I was at IIT where I was an engineering physics student in for 1 year and had secured 9.8% CGPA before dropping out to pursue MBBS from AIMS Raipur. So that's all about me. And before we begin, two things. First is if you guys will be interested and inspired by this free live sessions on YouTube, and if you want personalized one-to-one sessions for your entire NEET or JEE preparation, then uh, with personalized guidance, one-to-one guidance, and regular tests and assessment and discussions. Then you can contact on the number given below in the description of this video and get enrolled in our batches for live one-to-one lectures. And one other thing that if anyone has any doubt uh, in any of the solution, in any part of the solution, then you can type it in the comment section in the YouTube below. I'll check the comment section after solving each of the every question. Then I'll take up the doubts and try to dissect and uh, clear clear them. So yeah, so let's start the session without further delay. And here is the first question right in front of us. Let's read through the question statement. This figure 8.5, uh, shows a capacitor made up of two circular plates. This is one plate, this is the other plate, each of radius, which is 12 centimeters. Okay. And they are separated by a distance of 5 centimeters. So, what the question is saying, this radius is 12 centimeters. This radius is also 12 centimeters. And this distance of separation is 5 centimeters. Okay, all right. So this much has been given to us. Next, the capacitor is being charged by an external source, which is not shown in the figure. Okay, and the charging current is constant and is equals to 0.15 ampere. So we have a charging current over here, which is 0.15 amperes. So this much information has been given to us. Let me write this in a better way. Uh, 12 centimeters, 12 centimeters. Okay. So let's dive in into the first bit of the question, which says, calculate the capacitance and the rate of change of potential difference between the plates. So, uh, first of all, the capacitance of any parallel plate capacitor, uh, everyone knows the formula is epsilon naught A upon B, right? Where epsilon naught is the permittivity of free space, A is the area of the cross-sectional area of the parallel plate, each of the parallel plate, and D is the separation between the plates. Okay, so plugging in the values, epsilon naught has the value 8.857 into 10 raised power minus 12 into area of each of the plate. This is a circular plate with a radius of 12 centimeters or 0.12 meters in SI units. So the area will be pi r square, right? Pi into 0.12 squared in SI units upon the distance between the plates, which is your 5 centimeters or 0.05 meters. 0.05 meters. So if you solve this in a calculator, you'll have 8.0032 into 10 raised power minus 12 farads, which is the SI unit of capacitance. Okay. And so this should equal to 80.032 picofarads. Okay. So this is the capacitance which we found out. And then we need to find the rate of change of potential difference between the plates. Okay. So charge on each plate, which is Q, okay, Q should equal, this is 10 raised power minus 11. Picofarads is 10 raised power minus 12, right? Okay. So the charge Q on each plate of a parallel plate capacitor is given as Q equals CV, right? Everyone knows this equation where V is the potential difference across the plate. Now we need to find the rate of change of this V. So we'll differentiate this equation with respect to time. Okay, that implies dq upon dt equals C is constant, capacitance remains constant. So C dV upon dt, right? And this dq upon dt, as everyone knows, is basically the current passing through the circuit. Okay. So that implies this equation C dV upon dt equals the current. Okay. And we need to find the rate of change of potential difference, that is dV upon dt, right? Which is I upon C. We have been given the value of current in the circuit, which is 0.15 amperes. Okay. So let's plug in the value 0.15 upon the value of capacitance, which was 80.032 picofarads into 10 raised power minus 12. So if you solve this, you get 1.87 into 10 raised power 9 volts per second, the rate of change of potential difference, right? So this was the answer here, and this was the answer here. Okay. So the first bit is solved. Again, we found the capacitance epsilon naught A upon T. Okay. And we knew that Q equals CV. So differentiating with respect to time, dq upon dt is C into dv upon dt. And dq upon dt is just the current. So C dv upon dt is the current. So dv upon dt is I upon C. Reflecting the values and we arrive at the answer. Next, let's read out the second question or the second bit. Obtain a displacement current across the plates. So this is a fact which you should know, that the displacement current across the plates is actually the same as the conduction current, that is the current which is coming in and going out through here. Okay. So for the second bit, the displacement current is equal to the conduction current equal to the conduction current, which is 0.15 amperes, which is given to us. Okay, so there is no rocket science in here. Okay, so let's move on to the third bit of the question here. Is Kirchhoff's first rule, that is the junction rule, valid at each plate of the parallel plate capacitor? Explain. So first of all, let's understand what is the Kirchhoff's first law. Kirchhoff's first law says, uh, Kirchhoff's first law states that if we have a junction, okay, here, and a junction means that many currents or current carrying wires are actually meeting here, okay? And there can be currents which are coming into the junction, okay? And there can be currents which are going out of the junction, okay? Or away from the junction. So the Kirchhoff's first law says that the sum of the currents which are incoming, okay, or the currents which are coming to the junction should be equal to the sum of the currents that are leaving the junction. Okay. Or in other words, in this figure, we have I1 plus I2 plus I3. These are the currents which are coming into the junction. Okay. Should be equal to the currents that are leaving the junction, which is I4 plus I5. So basically, here actually there is an interesting concept known as a pseudo vector. Okay, so I hope you understood the Kirchhoff's first law. Okay, uh, then I'll just introduce you to the concept of a pseudo vector. A vector is something which has both magnitude and direction, right? In this case, we are considering the direction of the current, right? Because the incoming current and the outgoing current, okay? The current has some definite direction in this case. Or in any case, in any circuit, we always mention the direction of a current, right? Current is flowing to the left or right or wherever. But while adding currents, okay, if while adding currents, I just added their magnitudes, the incoming current and the outgoing current, right? I just added their magnitudes without taking in account the angle between them, right? Or I didn't add them as vectors, as conventionally vectors. I added them as a scalar, right? But I'm also taking into account the direction also. So this is the concept known as a pseudo vector, okay? It's not a true vector or doesn't get added up in pseudo vector, okay? So the example of a pseudo vector is actually the electric current, okay? So that's why when you actually define the vector quantities, the actual definition is a vector should have a magnitude, it should have a direction. Okay. We generally stop here, but there is a third component to it, which is it should obey the vector laws of addition. Okay. It should obey the vector laws of addition, like the parallelogram law and the triangle law, right? Otherwise, if a quantity has only these two, magnitude and direction, but it doesn't obey the vector laws of addition, it just gets added up like a scalar quantity, like in this case, the electric current, it's the pseudo vector. Okay. So for a pseudo vector, this point is not there. Okay. So back to the topic. So in this case, we said that the displacement current is equal to the conduction current, right? Or if I denote it, if this is one plate of the capacitor, okay, and here came the conduction current. Here came the conduction current. And uh, here I have the displacement current. Okay. Uh, Between the plates, I have the displacement current. I said that this conduction and displacement current are equal, right? The conduction current is equal to the displacement current. This has been found out. Okay. So that's why if I can very well apply, this is only the Kirchhoff's first law, right? This is the incoming current or the conduction current at the plate, and this is the outgoing current, right? So and they both are equal. So yes, the answer to the question is yes, I can apply the Kirchhoff's first law here also. Okay, first law, second law, every law is applicable over here. Okay, so so we are done with the first question over here, right? All the three bits. I guess no one has any doubts up till this point. So let's move on to the next question. Okay, so hmm, let's read out the question statement first. Here also we are having a diagram. A parallel plate capacitor in this figure is made up of circular plates, okay, each of radius 6 centimeters. Uh, okay, so each of radius 6 centimeters. Okay, all right. And it has a capacitance of 100 picofarads, right? So 100 into 10 raised power minus 12, which is 10 raised power minus 10 farads. Okay. The capacitor is connected to a 230-volt AC supply. 230 volt means the RMS voltage is 230 volts. Okay, AC supply with an angular frequency of 300 radians per second. Okay, 300 radians per second. So this much information has been given to us. Now the first bit says, what is the RMS value of the conduction current? Okay, we found the RMS voltage, and for any alternating current circuit, we need to first find the impedance, okay, or the in this case, because it's only a capacitor, so we can find the capacitive reactance of the circuit first of all. Okay, so yeah, so the capacitive uh, reactance, which is chi of C equals 1 upon omega C, right? 1 upon omega C equals uh, 1 upon 1 upon 300 into your capacitance is 10 raised power minus 10. Okay, so it will be 10 raised power 8 upon 3. Okay, so yeah, upon 3. So this is the capacitive reactance of the circuit. Okay, and the conduction current, or the conduction current RMS value. Okay, the IRMS would be equal to your VRMS upon chi of C, or capacitive reactance. Okay, in AC circuits, this chi of C, or the reactance, actually acts as the voltage. Sorry, as the resistance. Just in case of, just like the Ohm's law in your current electricity. Okay, so that equals VRMS is given to us 230 volts. Okay, upon chi of C, which is 10 raised power 8 upon 3. Okay, so this will be 23 into 3 upon 10 raised power 7. Okay, so if you solve it, you get the answer as 6.9 into 10 raised power minus 6 amperes. Okay, In other words, the RMS value of the current or the conduction current in the circuit, okay, this conduction current in the circuit will be equals to 6.9 microamperes, okay. So this is the answer to the first bit, okay. I hope everyone is clear up to this point. Okay. Next, the second bit is the conduction current equal to the displacement current. So the answer is yes. Answer is yes. The conduction current is equal to the displacement current always, okay, is equal to the displacement current. Now the third bit, okay, the third bit, it says determine the amplitude of B or the magnetic field at a point 3 centimeters from the axis between the plates. Okay, at a point 3 centimeters from the axis. So this is the axis at a point 3 centimeters above the axis. Okay, we have to find the amplitude of the magnetic field. Okay, because electromagnetic wave is a oscillating wave. Okay, of electric and magnetic fields. So we need to find the amplitude of the magnetic field here. Okay, so okay, the magnetic field from your magnetism chapter, you know, for a current carrying wire. Okay, if I have a current carrying wire over here of current I naught. Okay, so the magnetic field due to a current carrying wire infinitely long at a distance r from it. Okay, in this case, it will be inside the paper, inside the plane of paper, and the magnitude would be mu naught I upon 2 pi r, right? Upon 2 pi uh, r square into r. Okay, this is the magnetic field which is present away from the axis of the parallel plate capacitor. Like this is the capacitor. Okay, this is the capacitor, and this is the axis of the parallel plate capacitor. Okay, and at some r distance from it, the magnetic field is given as mu naught I. I is this thing, which is the displacement current. Okay, this is the displacement current, mu naught I r upon 2 pi r square. So you need to know this formula. Okay. Ah, so you need to know this formula. So where mu naught is the permeability of free space, right? Okay. And this I naught will be your maximum value of the current. Okay. Because we've been asked the amplitude of B. So here the maximum value of the current would be root 2 times the RMS current, right? And R is the distance between the plates of the parallel plate capacitor, okay, which is given to us as uh, 3 centimeters, okay. So substituting the values, we have B equals mu naught, value of mu naught is 4 pi into 10 raised power minus 7. I naught is root 2 times the IRMS. My RMS was 6.9 microamperes. Okay, 6.9 into 10 raised power minus 6. We are not I not R. R is 3 centimeters. 3 centimeters upon 2 pi. Capital R is this radius of the circular disc, okay, which is given as 6 centimeters. Is 6 centimeters. So 6 into 10 raised power minus 2. We do the cancellations. This is 2. These two are cancelled. Okay. And this is again 2. This 2 cancel. So you will be left with root 2 into 6.9 into 10 raised power minus 13. Okay. So the amplitude of the magnetic field, okay, comes out to be 1.63 into 10 raised power minus 11 Tesla. Okay. So this is the answer to this question. Okay. So you need to remember this formula for this question, which is amplitude of the magnetic field will be this. And if they tell you to find the amplitude of the electric field, then you know this relation, right? E by B equals C. Okay, the speed of light. Okay, so from here you can now find out the amplitude of the electric field. Okay, so these two equations you need to know. So I hope this question is clear to everyone. So let's then move over to our next question. Okay, so the next question says, what physical quantity is the same for X-rays of wavelength uh, 10 raised power minus 10 meters, red light of wavelength this much, and radio waves of wavelength 500 meters. Okay. So what quantity is same for these three electromagnetic waves? So we have been given X-rays. Okay. We have been given red light, which is our visible range light. Okay. And we have been given our radio waves. Okay. So these three things we have been given to us. This has a wavelength of 10 raised power minus 10 meters. This is 6800 angstroms, and this is 500 meters. Okay. Uh, for any electromagnetic waves, we talk about three things. Okay. The wavelength, the frequency, and the speed. Okay. So we talk about three things for any electromagnetic wave: the wavelength, the frequency, and the speed of light, okay, or the speed of the wave. So let's compare now. We have been already been given that the wavelengths are different, okay? So this is not the answer in this question. Now, frequency, we know that X-rays, red light, and the radio waves fall at different points in the electromagnetic spectrum, and they all have different energies, hence frequencies, okay? So this is also not same. So what we are left with is C, which is the speed. And yes, we know that all electromagnetic waves, okay, travel at the same speed, travel the same recording is. Also not safe. 8.3 actually, middle of 8.3. Hello? Hello, sir? Hello? Hello, sir? Okay, okay, guys. So, really sorry for the interruption. Actually, from 8.3 onwards, the audio wasn't available. So, I'll just quickly explain 8.3 and 8.4 again. Okay. So 8.3, the question says what physical quantity is the same for X-rays, red light, and the radio waves of given wavelengths. Okay. So we have these three given to us. And for any electromagnetic wave, we actually describe this quantity that is lambda, that is nu, and c. Okay. And as you can see, the lambdas are different. X-ray, red light, that is visible light, and radio waves all fall at different parts of the electromagnetic spectrum, and they have different frequencies. Frequency is also not the same. But speed, which is constant for all, which is c. Okay. So all electromagnetic waves travel at the same speed in vacuum or air, that is c. So the answer to this question is the speed remains constant for all these three types of waves. Okay. Next, the question fourth was a plane electromagnetic wave travels in vacuum along the positive z direction. What can you say about the directions of the electric and magnetic field vectors? And if the frequency of the wave is 30 megahertz, what is the wavelength? Okay. So uh, we actually said that the direction of propagation of the wave is actually along the direction of E cross B. E cross B is the direction of propagation. Uh, E cross B is the direction of propagation of the wave. Okay. And we said that the direction of propagation is given as positive z direction. So what could be the possibilities for E and B? Okay. If E was along the plus y and B was along minus x, then E cross B could be along this plus z direction. And if E was along minus y and B was along plus x, then it could be along your positive z direction. Okay, so these two cases, E plus y, B minus x, and E minus y, B plus x. And both E and B wave should be in the xy plane. Okay, and the second bit was if the frequency is this much, then what is the wavelength? Frequency is 13 to 10 raised per 6 hertz, and we know the speed is always constant, okay, which is 3 to 10 raised by 8. So your lambda would be c upon nu, okay, which is 10 meters. So this was fourth question. And the fifth question, a radio can tune in to any station in 7.5 megahertz to 12 megahertz band. What is the corresponding wavelength band? So this was the frequency band, okay, 7.5 to 12 megahertz, the bandwidth, okay, and we know the speed is always constant, which is 3 to 10 raised by 8. So we found the corresponding wavelengths. If this is the minimum frequency, this should be the maximum wavelength, which is 40 meters, and this is the minimum wavelength, which is 25 meters, okay. So the wavelength band is between 40 meters and 25 meters. Okay. So this was the answer to this question. And this is the sixth question. which we were discussing that a charged particle oscillates about its mean equilibrium position with a frequency of 10 raised power 9 Hz. And what is the frequency of the electromagnetic waves produced by the oscillator? So, in this discussion, we actually discovered that there can be three possible situations for a charged particle. Either it could be at rest, either it could be moving at a uniform velocity and a zero acceleration, or it could be moving with a non-uniform acceleration or an accelerated charged particle under which your circular motion also comes. So in the first case, the charge only produces electric fields. In the second case, it produces electric current and your magnetic field. Okay. And in the third case, wherein it's an accelerated particle, it can produce electromagnetic waves or it can radiate energy in the form of electromagnetic waves. Okay. So in the question, we have been given that the particle actually oscillates. Okay. Now oscillates means if this is the main position, it goes back and forth. Okay. It oscillates. So an oscillatory motion, there is a change of velocity involved. And if the change of velocity, then it's always an accelerated motion. Okay. And an accelerated charged particle, as we said, radiates electromagnetic waves. So this will also radiate electromagnetic waves, and we are being asked what is the frequency of that electromagnetic wave. And we should know that the frequency is always equal to the frequency with which it oscillates. Okay. And that is 10 raised power 9 hertz or 1000 megahertz. Okay. So I guess this question is clear to everyone. Okay. So let's then move on to the next question. Okay. The amplitude of the magnetic field part of a harmonic electromagnetic wave in vacuum is B naught equals 510 nanoteslas. Okay. So what is the amplitude of the electric field part of the wave? So the magnetic field amplitude is given as 510 nanoteslas, which is 510 into 10 raised power minus 9 teslas. Okay. And we know the relation between the electric and magnetic field is E naught upon B naught always equals the speed of the electromagnetic wave. Okay, so this relation you should know. So from here we can find the amplitude of the electric field component, which is CB naught. Okay, C is uh, in vacuum. So 3 into 10 raised power 8 into 51 into 10 raised power minus 8. Okay, so this equals 153 newtons per coulomb, right? These two cancel out, right? So this is the answer to this question. This is the amplitude of the electric field component. Okay. So this formula you should know the relation between the electric field and the magnetic field component. All right. So now let's move on to the next question, which says, suppose that the electric field amplitude, okay, E naught of an electromagnetic wave is E naught equals 120 newtons per coulomb, and that its frequency is this much. Okay, that is 550 megahertz. All right. And we have to determine all these four quantities and write the expression for your electric and your magnetic field. Okay. So in the first bit, we have been given the amplitude of the electric field is 120 newtons per coulomb. Okay. And its frequency is 50 megahertz, that is 50 into 10 raised power 6 hertz. So we know E naught upon B naught is C. Okay. So that implies your B naught will be E naught upon C, which is 120 upon 3 into 10 raised power 8. Okay. So this is 40. And this is 4 into 10 raised power minus 7 Teslas. Okay. So this is the amplitude of the magnetic field. Okay. Or this is 400 nanoteslas. Okay. All right. Now we have to find, we know C and we have nu, so we can find your lambda. Okay. Which would be C upon nu, which is 3 into 10 raised power 8 upon 50 into 10 raised power 6, which is 3 upon 5 into 10, which is your 6 meters. Okay, so this is answer. This is the answer of wavelength. Okay, then we have to find the wave number, that is the K. K is wave number, which is 2 pi upon wavelength. Okay, 2 into 3.14 upon 6. So if you solve it, this comes out to be 1.05 radians per meter. Okay, this is the wave number. Okay, K is wave number. Okay, and the last thing is your omega, right? Omega conventionally everyone knows, which is 2 pi times your frequency, right? 3.14 into 5 into 10 raised power 7. Okay, so if you solve it, it comes out to be your 3.14, which is 2 times 3.14, right? So 3.14 into 10 raised power 8 radians per second. So this is the answer. So we found out all the four quantities. And the second bit is find the expression for E and B. Okay. Let's take this up in the next page. The second bit, find the expression for E and B. Okay. So let's suppose that the wave is propagating in the plus x direction. We have not been given any information about the direction. So we say that it is propagating in the plus x direction. Okay. So if the wave is propagating along the plus x direction, we can take the E vector in the y direction. Okay. And the B vector in the z direction. Okay. Because the direction of propagation should be E cross B. Okay. J cross K is I. Okay. So, okay. Now the equation of in general of an electric field in an electromagnetic wave is given as E naught sine kx minus omega t, right? And is this along the plus y direction? It will be j cap. So E equals E naught, which is the amplitude given as 120 sine k. We found out the wave number or the propagation constant, which is 1.05. Okay, so 1.05x minus omega angular frequency, which is 3.14 into 10 raised power 8. 3.14 into 10 raised power 8t j cap. Okay, this is the electric field vector. Okay, this is one possibility, and the magnetic field vector is given as P naught sine kx minus omega t plus z direction, so k cap. Okay, so B naught. Uh, the amplitude of magnetic field is 4 into 10 raised power minus 7 or 400 nanoteslas. Okay, So 4 into 10 raised power minus 7 sine 1.05 x minus 3.14 into 10 raised power 8 t k cap. Okay, so this is the answer to this question. Okay, next, moving on to the next question. The terminology of different parts of the electromagnetic spectrum is given in the text. Use the formula E equals h nu, okay, and obtain the photon energy in units of electron volts for different parts of the electromagnetic spectrum. In what way are the different scales of the photon energies that you obtained in the previous part related to the sources of electromagnetic radiation? Okay, so okay, so we have been given E equals h nu. H is the Planck's constant, which is 6.6 into 10 raised power minus 34 mu. Okay, and energy, this is in joules. Okay, so and we need to find it in electron volts. Okay, and we have been given in joules, so we need to divide it by your 1.6 into 10 raised power minus 19 times new electron volts. Okay, on that. Now, we have been given for gamma rays, okay, for each part of the spectrum we need to find out, right? So we'll first find for your gamma rays, okay? For gamma rays, actually, the wavelength ranges from 10 raised power minus 10 to 10 raised power minus 14 meters. Okay. So the energy we can write as Hc upon lambda, right? Into 1 upon 1.6 into 10 raised power minus 19 electron volts. Okay. So if you substitute, you will get this as 10 raised power 4 electron volts and this as 10 raised power 8 electron volts. Okay. For gamma rays. Now, similarly for X-rays, I'll just not write the calculation every time the X-rays. The wavelength ranges from 10 raised power minus 8 to 10 raised power minus 13 meters. So the energy is 100 electron volts, and this is 10 raised power 7 electron volts. Okay, this is for X-rays. Then for your UV radiation or your UV rays, the wavelength ranges from 4 into 10 raised power minus 7 meters till 6 into 10 raised power minus 7 meters, and hence the corresponding energy bands are 10 raised power 3 electron volts to 10 raised power 10 electron volts. Okay, so these are your UV radiation. Okay, then your option D is for your visible wavelength or your visible light, and visible light wavelength ranges from 4 into 10 raised power minus 7 to 7 into 10 raised power minus 7 meters. Okay, and this energy is 10 raised power 10 electron volts, and this is 100 electron volts. Okay, next for IR, for infrared radiations, We have from 7 into 10 raised power minus 7 meters to 7 into 10 raised power minus 14 meters. Okay. So this is from 100 electron volts to 10 raised power minus 3 electron volts. Okay. Then after IR, we have microwaves and your radio waves. Okay. So similarly, we can find for microwaves, it is from 10 raised power minus 3 electron volts to 10 raised power minus 6 electron volts. And for radio waves, it is 10 raised power minus 6 electron volts. Okay. And the photon energies for different parts of the spectrum of a source indicate the spacing of the relevant energy levels in the source. Okay, we had been asked in what way are the different scales of photon energies related to the sources? It refers to the spacing of the relevant energy gaps and energy gaps in the source. Okay. So this is the answer to this question. Let's move on to the last question for today, which is in a plane electromagnetic wave, the electric field oscillates sinusoidally at a frequency this much, at an amplitude this much. Okay. What is the wavelength of the wave? So we have been given the frequency of the wave 2 into 10 raised power 10 hertz. Okay. So the wavelength would be C upon nu, which is 3 into 10 raised power 8 upon 2 into 10 raised power 10. Okay. So this answer is 0.015 meters. Okay. Next, what is the amplitude of the oscillating magnetic field? Okay. So E naught upon B naught is C. That implies B naught will be E naught upon C, right? And E naught is given to us as amplitude is 48. 48 upon your C, which is 3 into 10 raised power 8. So it is 16, or you can write 1.6 into 10 raised power minus 7 Teslas, right? Or 0.16 micro Teslas. Okay. Now, the third bit is show that the average energy density of E field equals the average energy density of the B field. Okay. Now, the average energy density of the electric field is given as half epsilon naught E squared. And the energy density of the magnetic field averaged gives a half upon mu naught into B squared. Okay. Now, we know two relations that E upon B is C and C equals 1 upon square root of mu naught epsilon naught. Okay. So if I take UE upon UB, I'll get epsilon naught mu naught, okay, into E squared upon B squared. This will be equal to epsilon naught mu naught. E upon B whole squared will be C squared, right? And this will be 1 upon mu naught into epsilon naught, right? Because C squared will be 1 upon mu naught epsilon naught. So this is 1. That implies UE will be equals to UB, hence proved. So this is the answer to this question. So I guess with this, we are done with all the questions for today. Uh, Let me check the YouTube comment section once for any doubts. If people are having. So so I guess with this, we are done with all the questions for today. Uh, okay, so in the comment section also, there is no doubt. So I guess with this, we are done for today. Before leaving, I'll just implore you again that if you guys are interested for one-to-one dedicated live lectures and personalized doubt solutions, then you can contact for your NEET and JEE preparation. You can contact the contact number given in the description box below, and join us for your full-fledged NEET and JEE preparation. Okay, so bye for today. Till next time. And thank you everyone for your patient hearing.